Well, I think the trouble with string theory is that there isn't any connection with observations. As far as I'm probably taking too strong a view here, but the mathematics, I mean, it's largely driven by the mathematics as far as I know, which is in itself is not an objection as far as I'm concerned. A lot of what I do is driven by the mathematics. But the trouble with string theory is it's supposed to be a theory of the way the world operates. And if the number of dimensions of space is just wrong, I can't take it seriously.
British mathematician and philosopher Sir Roger Penrose and American theoretical physicist Michio Kaku hold significant positions in the scientific community. Penrose is acclaimed for his contributions to understanding black holes, while Kaku is recognized for his work on string theory. What's intriguing, though, is Sir Roger Penrose's firm disagreement with Michio Kaku's string theory. Dark matter plays a crucial role in explaining certain phenomena in the universe. However, Penrose posits that dark matter may not exist at all. So what motivates Penrose to oppose Michio Kaku's string theory, and why does he assert the non-existence of dark matter? Let's delve into the reasons. Our universe is made up of matter, breaking down into particles upon closer inspection. These particles, like electrons, quarks, and neutrinos, travel through the universe, interacting by exchanging other particles. The Standard Model, our current precise mathematical description of the quantum world, accounts for these diverse particles. It includes fermions, primarily forming matter, and bosons, mainly describing interactions. Initially, it might seem like the ultimate theory, encompassing everything. However, there's a hitch. It fails to address gravity on a large scale. General relativity describes gravity, where objects curve spacetime, attracting others. We expect that the curvature of spacetime at the quantum scale involves tiny particles called gravitons. Yet, when attempting to integrate the graviton into the Standard Model, calculations yield absurd infinite values. Describing gravity at the quantum scale becomes elusive. Enter string theory, a concept that emerged over half a century ago. Instead of particles as dimensionless points, string theory posits that they are tiny strings, sometimes open and sometimes closed, vibrating like tiny rubber bands. These vibrations produce different particle types, including gravitons. Starting with the premise that particles are tiny strings, we explain the existence of various particle types and predict the graviton, addressing quantum gravity. Now let's explore how these strings evolve in the universe. Using the same principles as current models, we launch an electron toward a target. At the quantum scale, this experiment can yield different results, and physics aims to ascertain these probabilities. In string theory, particles are no longer depicted as points, but as strings tracing surfaces. To describe a string's probabilistic evolution, we consider all possible geometries it can trace over time. By summing up these scenarios, string theory inherently incorporates interactions without manual addition, resolving previous issues. While promising, the theory faces problems. Superstring theory, an extension introducing spinors on strings to describe fermions, solves two issues but introduces a third: the required 26-dimensional universe. Despite advancing to a 10-dimensional universe, a mismatch with our 4-dimensional reality persists. Possible solutions include our universe as a 3-dimensional slice of a larger one, or the 6 unobserved dimensions being compacted and minuscule. Though speculative, these ideas suggest observable phenomena, such as massless particles moving at the speed of light partially traversing compact dimensions. The multitude of possibilities raises questions about why our universe contains the particles of the Standard Model. Speculative hypotheses suggest a changing geometry over time, altering the laws of physics during the universe's early stages. String theory remains challenging to experimentally test due to the tiny scale of strings. Despite being speculative, it is one of the most promising models, describing quantum-scale gravity, enhancing our understanding of the Standard Model, and proposing particles like actions as potential explanations for dark matter. However, extensive research is needed, and aspects of string theory best understood rely heavily on supersymmetry, suggesting the existence of yet unobserved particles. There are 5 versions of superstring theory, mathematically approximating an 11-dimensional universe. Now, let's delve into why Roger Penrose contends that cosmic inflation is merely a fantasy. The concept of cosmic inflation is a hypothesis designed to elucidate specific observations of the early universe. Penrose's stance derives from his alternative proposal called conformal cyclic cosmology, CCC, offering a unique viewpoint on the origins and evolution of the universe. In Penrose's conformal cyclic cosmology, the idea of an inflationary phase is questioned. While cosmic inflation suggests a rapid early expansion of the universe, addressing certain issues of observed uniformity and flatness, Penrose argues that this model introduces more questions than it resolves. One of Penrose's primary critiques revolves around the insufficient explanation for the initial conditions required for inflation to occur. Inflationary models often hinge on the assumption of a primordial scalar field driving the expansion, but the origin and properties of this field remain largely speculative. Penrose questions the plausibility of such assumptions, suggesting they may be overly contrived. Another concern raised by Penrose is the measure problem within the inflationary framework. Inflation predicts a multiverse, a vast ensemble of universes with distinct properties and physical laws. However, determining the probability distribution of universes within this multiverse and explaining why we observe specific physical laws and constants becomes challenging. Penrose argues that this lack of predictive power undermines the scientific rigor of inflationary cosmology. Additionally, Penrose's conformal cyclic cosmology offers an alternative to the Big Bang singularity, proposing a cyclic series of expansions and contractions. According to this model, the universe undergoes eons, each preceded by a conformal phase erasing remnants of the previous universe. In Penrose's perspective, this cyclic nature eliminates the necessity for an inflationary phase to account for the observed uniformity and flatness of the universe. Now let's delve into Roger Penrose's research on black holes. Penrose's investigation traces back to the 1960s when he collaborated with Stephen Hawking to formulate the singularity theorem, mathematically confirming the existence of singularities within black holes, areas of infinite density and curvature where the laws of physics break down. This groundbreaking effort laid a sturdy groundwork for black hole study, solidifying their theoretical existence. One of Penrose's key contributions is the Penrose process, suggesting the potential to extract energy from a rotating black hole. According to Penrose, if an object enters the ergosphere, a zone outside the event horizon, but within the outer boundary of a rotating black hole, it can split, with one part falling into the black hole and the other escaping with increased energy. This concept implies that black holes could function as vast power sources, tapping into the immense rotational energy they store. Alongside the Penrose process, Penrose introduced the concept of cosmic censorship. This hypothesis proposes that singularities within black holes are perpetually concealed from external observers by an event horizon, a boundary beyond which no information or signals can escape. While cosmic censorship remains an unresolved question, Penrose's work has sparked extensive research and debate on this intriguing topic. Furthermore, Penrose's research on trapped surfaces has significantly contributed to black hole studies. Trapped surfaces are space-time surfaces that can trap light rays, preventing their escape. These surfaces play a vital role in gravitational collapse, where matter compacts until it forms a singularity within a black hole. Penrose's work on trapped surfaces has offered valuable insights into the dynamics of black hole formation and has contributed to our understanding of the cosmic phenomena associated with them. Another noteworthy facet of Penrose's black hole research is the proposal of the cosmic no-hair conjecture. This conjecture suggests that the only enduring properties of a black hole after its formation are its mass, electric charge, and angular momentum. According to this notion, the specific details of the matter forming the black hole do not have a lasting impact on its external properties. The cosmic no-hair conjecture has played a fundamental role in simplifying the study of black holes, enabling researchers to concentrate on their macroscopic features. Now let's explore arguments suggesting that dark matter might not exist. While its existence is widely accepted in the scientific community, ongoing debates and alternative hypotheses challenge this consensus. One argument against dark matter suggests that the observed gravitational effects attributed to it could be explained by modifying our understanding of gravity. Proponents of modified gravity theories argue that our current grasp of gravitational forces may be incomplete, proposing changes to the laws of gravity to explain observed phenomena without invoking dark matter. Another argument questions dark matter due to the lack of direct observational evidence. Despite extensive efforts, no direct detection of dark matter particles has been made to date. Various experiments, including those involving particle detectors and underground laboratories, have been conducted in the search for dark matter particles, but none have provided definitive evidence. Critics argue that this absence of direct detection casts doubt on the existence of dark matter as a distinct form of matter. Some researchers suggest that observed gravitational effects attributed to dark matter could be the result of other astrophysical phenomena, like gravitational interactions between visible matter within galaxies. This perspective implies that our understanding of visible matter dynamics might be incomplete, or other astrophysical mechanisms are at play. Critics question dark matter's role in explaining certain observations, proposing alternative explanations, such as modifications to the distribution of visible matter. It's essential to note that arguments against dark matter are not widely accepted within the scientific community and are subject to ongoing debate. While many consider dark matter the most compelling explanation for various phenomena, alternative perspectives continue to be explored. Observations and simulations strongly support dark matter's existence as a significant component of our universe. Despite critiques, dark matter remains the prevailing hypothesis that best fits available evidence, providing a consistent explanation for astrophysical observations. If dark matter does not exist, it would challenge our current understanding of the universe, its gravitational effects on visible matter, and the cosmic microwave background have inferred its presence. Dark matter explains rotation curves of galaxies, the large-scale structure of the universe, and gravitational lensing effects. Without it, scientists might need to revise gravity theories and rethink the early evolution of the universe. The absence of dark matter raises fundamental questions about our understanding of cosmic structure formation. So, that wraps up this discussion. If you found it insightful, give it a thumbs up and share your thoughts in the comments. Stay tuned for more. Thanks for watching.